Hello, and welcome to Boring Quantum Mechanics for Sleep. I know what you're thinking. Quantum mechanics, that sounds anything but boring, and you're right. It's a world of mind-bending ideas, of bizarre paradoxes, and of scientists who were as eccentric as their theories. We'll explore the history of this fascinating field, not as a dry textbook lecture, but as a story of brilliant minds, heated debates, and discoveries that changed the course of human history. I'd love for you to do me a small favor. Just gently type out in the comments where you're listening from and what time it is for you. It's always a pleasure to know who I'm sharing these stories with, creating a small, connected community in this vast universe. Tonight, we're not aiming for a deep, rigorous understanding of quantum mechanics. We're simply going to drift through its history like a gentle stream, carrying us through the lives and ideas of the remarkable people who shaped it. So close your eyes, take a deep breath, and let your mind be open to the wonderfully weird world of the quantum. Our story begins not with a bang, but with a puzzle. A seemingly simple question that baffled physicists at the end of the 19th century. It was a time of great confidence in the world of physics. They had Newton's laws of motion, which could predict the movement of planets with stunning accuracy. They had Maxwell's equations, which beautifully described the behavior of light, electricity, and magnetism. It seemed like the grand edifice of physics was nearly complete, with just a few minor details to tidy up. One of those minor details was something called the ultraviolet catastrophe. It sounds dramatic, doesn't it? Like a superhero movie title. But it was a very real and very frustrating problem. It had to do with something called blackbody radiation. Imagine a perfect black box. It absorbs all the light that falls on it. When you heat this box, it starts to glow just like a piece of metal. When you put it in a fire, first it glows red, then orange, then yellow, and eventually, if you could get it hot enough, a brilliant blue-white. Physicists wanted to understand the relationship between the temperature of the box and the colors of light it emitted. Their existing theories, the ones they were so proud of, made a very strange prediction. They predicted that, as the box got hotter, it should emit an infinite amount of ultraviolet light and even higher energy radiation like X-rays and gamma rays. This was obviously wrong. If it were true, your oven would be a deadly radiation source every time you baked a pizza. This glaring discrepancy between theory and reality was the ultraviolet catastrophe. This is where our first hero enters the story, a quiet, conservative, and deeply religious man named Max Planck. Planck wasn't a revolutionary. He deeply respected the classical physics of his time, but the ultraviolet catastrophe bothered him. It was an itch he just had to scratch. For years, Planck wrestled with this problem. He tried every trick in the book, every mathematical sleight of hand he could think of, but the infinity just wouldn't go away. Finally, in a moment of what he later called an act of desperation, he decided to try something completely radical. He proposed that energy, the very thing that was causing all the trouble, wasn't continuous. He suggested that it could only be emitted or absorbed in discrete little packets, which he called quanta. It was like saying you can't have any amount of water you want. You can only have it in individual cup-sized portions. Imagine you're at a vending machine. You can't just get a continuous stream of soda. You have to buy it in discrete cans. Planck was saying that energy behaved in a similar way. The size of these energy packets, he proposed, depended on the frequency of the light. The higher the frequency, the bluer the light, the bigger the energy packet. With this one seemingly small assumption, the ultraviolet catastrophe vanished. His new formula perfectly described the glow of a hot object, but Planck himself was deeply unsettled by his own idea. He didn't really believe in these quanta. He thought of them as a mathematical trick, a temporary fix, until a real solution could be found. He had, in his own words, opened the door to a new world, but he was hesitant to step through it himself. He had no idea that his reluctant discovery would be the first spark of a revolution that would completely reshape our understanding of reality. He had laid the first stone of quantum mechanics, a field so strange and counterintuitive that it would make the ultraviolet catastrophe seem like a minor hiccup. And it all started with a glowing black box, while Planck was reluctantly introducing the idea of quanta. Another young physicist was about to burst onto the scene, a man whose name would become synonymous with genius. Albert Einstein. We often think of Einstein in his later years, the wise old man with the wild hair and the gentle eyes. But in 1905, he was a 26-year-old patent clerk in Bern, Switzerland. He had a comfortable but not particularly stimulating job, but his mind was on fire. In what is now known as his miracle year, Einstein published 4 groundbreaking papers that would change the course of physics. One of these papers took Planck's idea of quanta and ran with it. While Planck thought of his quanta as a property of how energy was emitted and absorbed, Einstein took it a step further. He proposed that light itself is made of these little packets of energy. He called them Lichtquanten, or light quanta. We now call them photons. This was a truly radical idea. For centuries, light had been understood as a wave, and for good reason. It does all the things that waves do. It diffracts, which is why you can see light bending around corners. It interferes, which is why you see those beautiful swirling colors in a soap bubble. The wave theory of light was incredibly successful, and now here was this young upstart patent clerk saying that light is actually a stream of particles. It seemed absurd. It was like saying that the waves in the ocean are actually made of tiny little pebbles. But Einstein had a good reason for this audacious claim. He used it to explain another puzzling phenomenon called the photoelectric effect. Imagine you shine a light on a piece of metal. If the light is bright enough, it can knock electrons out of the metal. These are called photoelectrons. The strange thing was, the energy of these electrons didn't depend on the brightness of the light. It only depended on the color of the light. If you shone a very bright red light on the metal, nothing would happen. But if you shone a very faint blue light, even a tiny flicker, electrons would be instantly ejected. This was impossible to explain with the wave theory. A wave's energy is related to its amplitude, its brightness. A brighter light should have more energy and should be able to knock out electrons with more force. But But that's not what happened. Einstein's particle theory of light explained it perfectly. He said that each photon of light carries a certain amount of energy, and this energy is determined by its color, or more precisely, its frequency. Blue light has a higher frequency than red light, so blue photons have more energy. To knock an electron out of the metal, you need a certain minimum amount of energy. A single photon of red light, no matter how many of them there are, simply doesn't have enough energy to do the job. But a single photon of blue light, even if there are very few of them, has enough energy to kick an electron out. It's like trying to knock over a bowling pin with ping pong balls. You can throw as many ping pong balls as you want, but you'll never knock it over. But if you throw a single baseball, you'll send it flying. The ping pong balls are like the photons of red light, and the baseball is like a photon of blue light. Einstein's explanation of the photoelectric effect was a stunning confirmation of Planck's quantum hypothesis, and for this work, not for his more famous theory of relativity, he would eventually be awarded the Nobel Prize in Physics in 1921. But the story of light wasn't over. Was it a wave, or was it a particle? The answer, as we'll see, was far stranger than anyone could have imagined. This was the beginning of one of the central mysteries of quantum mechanics: wave-particle duality, the idea that something can be both a wave and a particle at the same time. It's a concept that would baffle and inspire physicists for decades to come, and it's a perfect place for us to pause, to let that strange idea float in our minds as we drift a little deeper. The early days of quantum theory were a bit like the Wild West. There were these new, strange ideas floating around, but there wasn't a coherent theory to tie them all together. That began to change with the arrival of a Danish physicist named Niels Bohr. Bohr was a fascinating character. He was known for his brilliant mind, his love of soccer, and his sometimes maddeningly obscure way of speaking. He would often mumble and speak in riddles, leaving his colleagues to piece together his brilliant insights. In 1913, Bohr came up with a new model of the atom that incorporated the quantum ideas of Planck and Einstein. At the time, the prevailing model of the atom was the Rutherford model, which pictured the atom as a miniature solar system with a dense, positively charged nucleus at the center and tiny, negatively charged electrons orbiting it like planets. But there was a big problem with this model. According to classical physics, an orbiting electron should constantly be losing energy by radiating light. This would cause it to spiral into the nucleus, and the atom would collapse in a fraction of a second. But atoms are stable. The chair you're sitting on, the air you're breathing, it's all made of stable atoms. This is where Bohr's genius came in. He proposed that the electrons in an atom could only exist in certain specific orbits or energy levels. It was like saying that a planet could only orbit the sun at certain specific distances, and nowhere in between. An electron in one of these special orbits would not radiate energy and would not spiral into the nucleus. It was in a stable state. It could only jump from one orbit to another, and when it did, it would either absorb or emit a photon of light with a very specific energy corresponding to the difference in energy between between the two orbits. This explained another puzzle of the time: the atomic spectra. When you heat up a gas, it emits light, but not a continuous rainbow of colors, like a hot black box. Instead, it emits light at very specific, discrete frequencies, creating a pattern of bright lines called an emission spectrum. Each element has its own unique spectral fingerprint. Bohr's model explained this perfectly. The spectral lines were the result of electrons jumping between the allowed energy levels in the atoms of the gas. His model was a huge success. It was a major step towards a true quantum theory of the atom, but it was also a strange and somewhat arbitrary theory. It was a mishmash of classical and quantum ideas. It worked, but nobody really knew why. Why were only certain orbits allowed? What was so special about them? Bohr himself was a central figure in the debates that would shape the future of quantum mechanics. His institute in Copenhagen became a mecca for physicists from all over the world. It was a place of intense intellectual ferment where the brightest minds of the generation came to argue, to collaborate, and to try to make sense of the increasingly bizarre quantum world. One of the key figures at Bohr's Institute was a young German physicist named Werner Heisenberg. Heisenberg was a brilliant and ambitious young man, and he was deeply dissatisfied with Bohr's model of the atom. He felt that it was too pictorial, too reliant on classical concepts like orbits. He wanted a theory that was based only on things that could be observed, like the spectral lines of an atom. In 1925, while recovering from a severe bout of hay fever on the remote island of Heligoland, Heisenberg had a breakthrough. He developed a new mathematical framework for quantum mechanics that did away with the idea of electron orbits altogether. In its place, he used arrays of numbers called matrices. It was a very abstract and mathematical theory, but it was incredibly powerful. It could be used to calculate the energy levels of atoms and the intensities of their spectral lines with stunning accuracy. This new theory was called matrix mechanics. At around the same time, another physicist, an Austrian named Erwin Schrödinger, came up with a completely different but equivalent formulation of quantum mechanics. Schrödinger was a very different character from Heisenberg. He was a classicist, a philosopher, and a bit of a ladies' man. He was deeply uncomfortable with the abstractness of Heisenberg's matrix mechanics. Schrödinger's approach was based on the idea of wave mechanics. He proposed that electrons in an atom could be described as waves. He developed a beautiful equation, now known as the Schrödinger equation, that described how these waves behave. The solutions to the Schrödinger equation gave the allowed energy levels of the atom, just like Bohr's model and Heisenberg's matrix mechanics. So now there were two different quantum theories: matrix mechanics and wave mechanics. They looked completely different, but they gave the same answers. It was later shown that they were just two different mathematical formulations of the same underlying theory, but the interpretation of these theories was still up for debate. What did these waves represent? Schrödinger thought that they were the actual physical waves of the electron, that the electron was literally smeared out in a wave. But this interpretation had its own problems. It was hard to see how a smeared out wave could suddenly coalesce into a point-like particle when it was detected. This led to one of the most famous and most misunderstood concepts in all of quantum mechanics: Schrödinger's cat. Schrödinger came up with this thought experiment to show what he saw as the absurdity of the prevailing interpretation of quantum mechanics, the Copenhagen interpretation, which was championed by Bohr and Heisenberg. The Copenhagen interpretation says that a quantum system, like an electron, can exist in a superposition of all its possible states at once. It's only when we make a measurement that the system collapses into a single, definite state. So, according to the Copenhagen interpretation, an electron can be in multiple places at once until we look at it. Schrödinger thought this was ridiculous. To show how ridiculous it was, he imagined a scenario where the fate of a cat was linked to the state of a quantum particle. Imagine a cat in a sealed box. Inside the box, there is a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, the Geiger counter will detect the radiation and trigger the hammer to smash the vial of poison, killing the cat. Now, the decay of a radioactive atom is a quantum event. According to the Copenhagen interpretation, the atom is in a superposition of both decayed and not decayed states until we measure it. But if the atom is in a superposition, then the Geiger counter is also in a superposition of triggered and not triggered, and the hammer is in a superposition of smashed and not smashed, and the vial of poison is in a superposition of broken and not broken, and the cat is in a superposition of being both alive and dead at the same time. It's only when we open the box and look inside that the superposition collapses and the cat becomes either definitively alive or definitively dead. Schrödinger thought this was absurd. A cat is either alive or dead. It can't be both. He intended this thought experiment as a criticism of the Copenhagen interpretation, but over the years, it has become one of the most famous illustrations of the strangeness of the quantum world. The debate between Bohr, Heisenberg, and Schrödinger was one of the most intense and important in the history of science. It was a clash of different philosophies, different ways of looking at the world, and it's a debate that, in some ways, is still not fully resolved today. What is the true nature of reality at the quantum level? Is it something that only becomes definite when we observe it, or is there a deeper, hidden reality that we have yet to uncover? These are the questions that we'll continue to explore as we drift further into the quantum realm. The double-slit experiment and the role of the observer. The development of quantum mechanics was not just a story of abstract ideas and mathematical formulas. It was also a story of experiments that pushed the boundaries of what was thought to be possible, and that provided stunning confirmation of the strange predictions of the new theory. One of the most important of these experiments was the double-slit experiment. It's an experiment that has been described as the heart of quantum mechanics because it so beautifully illustrates the central mystery of wave-particle duality. The setup is simple. You have a barrier with two small slits in it. You shine a light on the barrier and you have a screen behind the barrier to see where the light lands. If light is a wave, you would expect to see an interference pattern on the screen. The waves passing through the two slits would interfere with each other, creating a pattern of bright and dark fringes. This is exactly what you see when you do the experiment with light. It's a classic demonstration of the wave nature of light. But what if you do the experiment with particles like electrons? You would expect to see two bright bands on the screen directly behind the two slits. After all, each electron should go through one slit or the other and hit the screen at a specific point. But when you actually do the experiment, something amazing happens. You don't see two bright bands. You see an interference pattern, just like you do with light. It's as if each electron is going through both slits at the same time and interfering with itself. This is the mystery of wave-particle duality in its most stark and beautiful form. But it gets even weirder. What if you try to figure out which slit each electron goes through? You can put a detector at each slit to see which one the electron passes through. When you do this, the interference pattern disappears. You just see two bright bands, as if the electrons are behaving like particles again. It's as if the very act of observing which path the electron takes forces it to choose a path. It's as if the electron knows it's being watched. This is a profound and deeply mysterious result. It suggests that the act of observation is not a passive process. It actively influences the reality that is being observed. It's a conclusion that has troubled physicists and philosophers for decades. What does it mean for reality to be dependent on our observation of it? Another key figure in the story of quantum mechanics is a French prince named Louis de Broglie. In 1924, de Broglie, in his PhD thesis, made a bold and imaginative proposal. If light waves can behave like particles, he reasoned, then maybe particles, like electrons, can behave like waves. It was a beautiful and symmetrical idea, but at the time, there was no experimental evidence to support it. It was pure speculation. But it was a speculation that would soon be confirmed in a dramatic way. In 1927, two American physicists, Clinton Davison and Lester Germer, were studying how electrons scattered off a nickel crystal. They were having a terrible time with their experiment. One day, a flask of liquid air exploded in their lab, shattering their vacuum tube and exposing the nickel crystal to air. To clean the crystal, they heated it. What they didn't realize was that this process changed the structure of the crystal, creating large, single crystal regions. When they resumed their experiment, they saw something completely unexpected. The scattered electrons were not coming off in all directions as they had been before. They were coming off in specific directions, creating a diffraction pattern, just like X-rays. It was a stunning confirmation of de Broglie's hypothesis. Electrons, which had always been thought of as particles, were behaving like waves. This discovery was a crucial piece of the puzzle of quantum mechanics. It showed that wave-particle duality was not just a property of light, but a fundamental principle of nature, applying to all matter. The story of Davison and Germer is a wonderful example of the role of serendipity in science. A lucky accident An unexpected result can sometimes lead to a breakthrough discovery, but it also takes a prepared mind to recognize the significance of that discovery. The 1920s were a golden age for quantum mechanics. The basic framework of the theory was laid down, and a flood of new discoveries and applications followed. But it was also a time of great upheaval in the world. The rise of Nazism in Germany in the 1930s had a devastating impact on the scientific community. Many of the leading physicists of the time, including Einstein, Schrödinger, and Bohr, were forced to flee their homes and their jobs. It was a dark time for science and for the world. But it was also a time when the strange and abstract ideas of quantum mechanics would be put to their most terrible and consequential test. The story of quantum mechanics in the mid-20th century is inextricably linked with the story of the Manhattan Project and the development of the atomic bomb. It's a dark and complex chapter in the history of science, and it's one that raises profound ethical questions about the role of scientists in society. The key to unlocking the power of the atom was the discovery of nuclear fission. In 1938, two German chemists, Otto Hahn and Fritz Strassmann, were bombarding uranium with neutrons. They were expecting to create new, heavier elements, but instead they found something completely unexpected. They found barium, an element that was much lighter than uranium. They were baffled by this result. They wrote to their former colleague, Lise Meitner, a brilliant Austrian physicist who had been forced to flee Germany because she was Jewish. Meitner, along with her nephew, Otto Frisch, realized what had happened. The uranium nucleus had split in two, releasing a huge amount of energy in the process. They called this process fission. The discovery of fission came at a terrifying time. The world was on the brink of war, and a group of émigré scientists who had fled from the tyranny of Nazi Germany were deeply worried about what would happen if the Nazis were to develop an atomic bomb. In 1939, a group of these scientists, including Leo Szilard and Eugene Wigner, convinced Albert Einstein to sign a letter to President Franklin D. Roosevelt, warning him of the danger and urging him to start a research program on atomic energy. This letter was the catalyst for the Manhattan Project, a massive, top-secret effort to build an atomic bomb before the Germans could. The project brought together some of the greatest scientific minds of the generation, including many of the pioneers of quantum mechanics. The scientific director of the Manhattan Project was J. Robert Oppenheimer, a brilliant and charismatic theoretical physicist. Oppenheimer was a complex and often tortured soul. He was a man of deep culture and refinement, with a love for poetry and philosophy, but he was also a man of immense ambition and drive. Under his leadership, the scientists at Los Alamos, a remote laboratory in the New Mexico desert, worked tirelessly to solve the immense scientific and technical challenges of building a nuclear weapon. They were driven by a sense of urgency, a fear of what would happen if they failed. The work at Los Alamos was a testament to the power of quantum mechanics. The entire project was based on the principles of nuclear physics, which is a direct application of quantum theory. The scientists had to calculate the critical mass of uranium and plutonium, the amount needed to sustain a chain reaction. They had to design the complex implosion mechanism that would compress the plutonium to a critical density. It was a monumental undertaking, and it was a success. On July 16th, 1945, the first atomic bomb was tested in the New Mexico desert. The test, codenamed Trinity, was a terrifying success. Oppenheimer, watching the explosion, famously recalled a line from the Hindu scripture, the Bhagavad Gita. "Now I am become death, the destroyer of worlds." The bombing of Hiroshima and Nagasaki in August 1945 brought an end to the war, but it also ushered in the nuclear age, a new era of fear and uncertainty. The scientists who had worked on the bomb were deeply affected by what they had created. Many of them, including Oppenheimer, became passionate advocates for the international control of nuclear weapons. The story of the Manhattan Project is a stark reminder that science is not a purely abstract pursuit. It has real-world consequences, and scientists have a responsibility to consider the ethical implications of their work. The development of the atomic bomb was a triumph of science and technology, but it was also a human tragedy. After the war, the focus of physics shifted. The big questions were no longer about the structure of the atom, but about the nature of the fundamental particles and forces that make up the universe. This new field was called particle physics, and it was a direct descendant of quantum mechanics. The physicists of this era were a new generation with a new set of tools and a new set of questions. They built massive particle accelerators, machines that could smash particles together at incredible speeds to probe the deepest secrets of matter. One of the key figures in this new era was Richard Feynman. Feynman was a brilliant and iconoclastic physicist known for his playful spirit, his bongo playing, and his incredible ability to explain complex ideas in a simple and intuitive way. Feynman was one of the architects of quantum electrodynamics, or QED, the quantum theory of light and matter. QED is one of the most successful theories in the history of science. It has been tested to an incredible degree of precision, and its predictions have always been confirmed by experiment. Feynman developed a beautiful and intuitive way of visualizing the interactions between particles using simple diagrams that are now known as Feynman diagrams. These diagrams have become an essential tool for particle physicists. Another giant of this era was Murray Gell-Mann. Gell-Mann was a man of immense intellect and erudition, with a passion for linguistics and natural history. He was also a fierce rival of Feynman. Gell-Mann brought order to the chaotic zoo of new particles that were being discovered in the 1950s and 60s. He proposed that many of these particles were not fundamental, but were made up of smaller, more fundamental particles, which he called quarks. The idea of quarks was a bold and speculative one, and at first, many physicists were skeptical, but over time, the evidence for quarks became overwhelming. We now know that quarks are the fundamental building blocks of protons and neutrons, and of many other particles as well. The theory of quarks and their interactions is called quantum chromodynamics, or QCD. It's the quantum theory of the strong nuclear force. The the force that holds the nucleus of the atom together, QED and QCD, along with the theory of the weak nuclear force, which is responsible for radioactive decay, make up what is known as the Standard Model of particle physics. The Standard Model is a triumph of 20th century physics. It describes all the known fundamental particles and forces, with the exception of gravity, with stunning accuracy. But the Standard Model is not the final word. There are still many mysteries that it doesn't explain. What is dark matter? The mysterious substance that seems to make up most of the matter in the universe. What is dark energy? The even more mysterious force that is causing the expansion of the universe to accelerate. And how can we unite quantum mechanics with Einstein's theory of gravity to create a single, unified theory of everything? These are the questions that are driving the research of physicists today, and they are questions that may lead to a new revolution in our understanding of the universe, a revolution as profound as the one that was started by Max Planck and his reluctant discovery of the quantum. As we come to the end of our journey through the history of quantum mechanics, it's worth taking a moment to reflect on what we've learned. We've seen how a simple puzzle about the glow of a hot object led to a complete rethinking of the nature of reality. We've met a cast of brilliant and eccentric characters, from the cautious Planck to the flamboyant Feynman. We've explored a world of strange and counterintuitive ideas, from wave-particle duality to Schrödinger's cat, and we've seen how these ideas have had a profound impact on our world, from the development of lasers and computers to the unleashing of the terrible power of the atom. The story of quantum mechanics is a story of human curiosity, of our endless desire to understand the world around us. It's a story of struggle and triumph, of collaboration and conflict, and it's a story that is still being written as you drift off to sleep. Perhaps you can imagine yourself as one of these explorers, venturing into the strange and wonderful world of the quantum, a world where particles can be in multiple places at once, where reality itself seems to depend on how we look at it. It's a world that is far removed from our everyday experience, but it's also the world that underlies everything we see and touch. It's the world that makes the stars shine, the flowers bloom, and the gentle rhythm of your own breathing possible. So relax, let go of the day's worries, and let the gentle mysteries of the quantum world carry you off to a